Good afternoon, everyone. Uh, Today, my talk is on nanotechnology in VLSI, a bird's view. So, am I audible, sir? Am I audible clearly?
Madam, you are audible.
Thank you, sir. So, before I approach how this nanotechnology is impacting the VLSI designs, the chip design or integrated circuits, first of all, let us understand where we are standing on a scale. So if you see here, you can observe there is a macro scale, there is a micro scale, and there is a nano scale. So here you can see the macro scale, we are able to see with our naked eye. Any object which we are seeing able to view with our naked eye, that comes under macroscopic scales. Micro scale, it is not visible directly. We require some kind of special equipment in our hand to visualize them. So we are dependent on light microscopes to see them very clearly, to observe them very clearly. And coming to the nanoscale, so there we come across the DNA, the proteins in our body, the bacteria, the virus. So, which we require again a special equipment, kind of electron microscope to see them. So this is the range which I am showing here. So here you can see the range is from 0.1 nanometer to nearly 1 meter I have presented here. So here the light microscopes comes on up to 100 nanometers, but from 1 to 100 nanometers, we have to have an electron microscope to see them. So first of all, what is a nanomaterial? Why it is difficult to see them? Because nanomaterial is having a dimensions of in the range of 1 to 100 nanometers. So 1 nanometer means 1 into 10 power minus 9 meters. So 10 power minus 9 meters means you can see 0.801 meter. So that is the size of the particle. That is the size of the particle. So you can see here there are several objects or several bacteria, virus, and DNA structures, blood cells. Everything was present inside our body, outside the environment also. Maybe we are not aware of it. We are not aware of it. So here, the 1 nanometer, you can see there is a hair, the human hair, the dog hair, the fur, which is present on the bear or any kind of animal. You can consider them as the nanometer scale. Then, and you, as you are approaching towards the different scales, you can see the DNA, the proteins, the carbon nanotubes, the silver nanoparticles. So you know about the silver. Silver is a most antibacterial. So silver is a most antibacterial material or metal. So that's why our elders, forefathers tells us that you eat in the silver plates, silver glasses, since although you are not, your immune system will be developed as the days are passing when you take this silver nanoparticles. And virus. So all of you are very well aware of the virus because a couple of years we have suffered from the coronavirus. It has been multiplied, it has been strengthened. No device is able to visualize them nor able to decrease their strength, rather than we have increased our immunity to fight it out. So this kind of virus, everything is present in between 1 to 100 nanometers scale. So this coming to the micron, you require only light microscope. So this is about a scale which is majority of the objects which I have presented here. Already we are aware of it. Daily we are seeing them. Daily we are living with them. Daily we are living with them. So there are several applications of these nano materials here. Several. You can take any kind of industry: textile industry, electrical industry, healthcare, food, agriculture, electronics, or you take environmental, or you consider any of the industry. You have so many number of applications. Only thing is we have to explore, evolve, and get into that area to really understand at fundamental level what is actually happening, what is actually happening in the material level or at the atomic level. So why the small is good? Why we are running across this? Why we are running across this nano materials? Why we are running across this nano materials? Because nano objects are faster, nano objects are lighter, can get into small spaces, cheaper, more energy efficient, different properties at a small scale. The two important properties, what is making it different from the macro and microscopic materials are: surface area increases as the size decreases. For example, I have presented here a table where you can see the balls. You can think of a football or any kind of a ball here, where the number of atoms, there are seven spherical shells are there. The total number of atoms which are present is 1415, and on the surface only 35 atoms are present. So see, the surface, more number of atoms are present on the surface, more reactions, more hyperactive conditions will be taking place. So the number of shells are decreased. The what do you say? The total number of atoms are decreased, but the number of atoms on the surface are increased to 45. So as the number of shells are decreased, the size of the shells are decreased. So what is happening? The total number of atoms present inside the balls are also, or what do you say, is decreased, but the surface atoms are increased. So as the surface, sorry, as the surface is as the number of shells are decreased, the surface atoms are increased to a very large number. So the as the size is decreased, the number of atoms which are present on the surface is increased. Thereby, the reactions or the what do you say, the way it is merging will be more actively participating in any kind of device or in any kind of reactions. So this is a one property which is making it different. Surface area increases as the size with respect to the size. Then coming to the second one is the quantum confinement. It is one of the second property which is making it different again from the micro scale and macro scale. As the all of you are aware of the semiconducting materials. So semiconductors, we know that in the semiconductors there will be a valency band, there will be a conduction band, there will be a band gap, everything will be there. But as you are decreasing the size of the atom, the band will be shrinking, and the narrow band gap will be happening between the conduction band and valency band. So as the size of the atoms in the valency band or conduction band is decreased, you can see more and more number of atoms will become light, more and more number of atoms will be participating, and the band gap will be increasing. The band gap will be increasing in the molecule. So this one aspect is defined as a quantum confinement. This quantum size effect occurs when the nanostructures themselves become smaller at the fundamental scale. So where here I can give one more example. Gold, all of you are aware of the gold, how the gold coin will look like. It is in yellow color. It is a yellow color, but the same gold particles, that is AU, right? That is the chemical name of the gold. So when you are taking the gold particles at a macroscopic scale, it is in the shape of yellow metal. It is an yellow metal, but when you are taking that gold in the nano range, the color is changed to red color. The color is changed to red color because of the changes in the atoms, changes in the material properties when it goes to the size, when it goes to the nano size. So these nanomaterials are divided into actually 4 dimensions. One is a 0 dimension, one is 0 dimension, one is second one is 1 dimension, 2 dimensions, 3 dimensions. So these nanoparticles are divided into more or less into the 3 categories. We say the 1 dimension means any one parameter. You take a cube, there will be length, there will be breadth, there will be height, right? If the one length is in the nanometer range, then we say that they are one-dimensional nanomaterials. If the 2 dimensions are in the nano range, like length and breadth both are in the nanometer range, and height is not in the nanometer range, height is in some other scale, it is not in the nanoscale, then we say that it is in the 2 dimensions. And 3 dimensions means all the 3 parameters, you take length, breadth, and height, they are defined as a 3 dimensional nanoparticles. For example, you can take it as a wire, a scale, and a mesh, and you can consider them as a ball in 3 dimensional space. Coming to the 0 dimension, there is one more dimension which we say 0 dimension, like a dot, 0 dimension. So these 0 dimensional nanoparticles, we say if the size of the particle is in the range of 1 to 10 nanometers, out of 1 to 100, if the size of the nanoparticle is in the 1 to 10 nanometers, then we say that they are 0 dimension. The best example for here it is a quantum dots. The best example here it is a quantum dots, because the quantum dots are used mainly in the medical device applications. They are used as a targeted drug deliveries, especially in the cancer treatment, especially during the chemotherapy, during the cancer treatment. The research is going on to devise a medical device, or to have a medicine with using the quantum dot particles. So when we have a 1 to 10 nanometer size for any particle, we say it is in the 0 dimension and it is in the quantum dimension. So now different types of nanomaterials. So what are the different types of nanomaterials? We can see these nanoparticles, naturally occurring nanoparticles, like forest fires, when the forest fires, sea sprays, mineral composites also you can see, and volcanic ash, and viruses. So virus, I think all of you have a best, what do you say, the known about this viruses nowadays, because we have gone through that kind of tough phase couple of years because of this virus. So this, they are naturally occurring nanoparticles. If we measure the size of the particles in all these areas, we will get in the range of 1 to 100 nanometers. Nowadays, recently, you can think of headlines in the Delhi. In the Delhi, the dust is coming. The pollution, the pollution. They have checked the pollution, and the pollution consists of dust particles which are in the nano range, so that means it is a very dangerous one, because they can go into our skin, they can damage they can damage the organs of our body also, because the skin pore is large when compared to the nanoparticle size. So they can easily go into our skin and can affect our body also. So the different types of nanomaterials, like when you make some kind of experiments, or when you are doing some kind of works at home, like cooking smoke, diesel exhaust, welding fumes, industrial wastage when it is coming through the pipes, or sand blasting, you will get a lot of dust. So there the particles are again in the nano range. The dust particles, or the fumes, or the gases which are coming in these conditions, incidental. They are from the human origin, because of the works which we are doing. The different types of exhaust airs and gases are coming out to the surroundings. Now coming to the next type of particles, these are engineered made nanoparticles. Like we are particularly working in the lab and making the nanomaterials. We are particularly, like you work in the lab, like physics lab, chemistry lab, electrical lab, electronics lab. You do some kind of experiments like that. If we do some kind of experiments by getting some kind of reactions, we are forcefully making the using the elements, chemicals, and preparing the nanomaterials. These are human origin, but engineered nanomaterials, engineered nanoparticles, more variable. Whatever the shape you want, you can prepare them. Whatever the size you want, you can prepare. You can impose the conditions. You can have that kind of environment. You can provide that kind of conditions and environment to get whatever the size and shape of the nanoparticles, nanomaterials you want. Now coming to the mainly the nanotechnology. So what it is exactly ruling us, how it is exactly ruling the devices or ruling the areas. So if you take the nanotechnology, it is the nothing but making the material at the nanometer scale, that is 1 to 100 nanometers. So to create materials, to create structures, to create devices also you can use devices, you can make the systems and sensors. So here you can especially the VLSI, very large scale integrated circuits, very large scale integrated areas are much more related to this devices and systems. First of all, these three are actually interconnected to each other. If you prepare a material and that material is used in the making of a device, and that a lot of devices are used in making a system to work, then you are using the technology that is nothing but nanotechnology. Okay. So now coming to the, what do you mean by integration? So all of you are aware of that, but just I would like to give a glance of this integration part. An integrated circuit is a chip or microchip. So you have a lot of transistors when you are taking when you are talking about a motherboard in any kind of a mobile phone or in any kind of an electronic device. Any device you take, you should have the integrated chip. You should have an integrated circuit board. So without this integrated circuit board, the device cannot function. It is like a heart of the human body. Like that, integration also acts as a heart of the system, heart of the device. So it consists of several active. So what we actually use on this system, we use several active and passive components like resistors, capacitors, and active components such as transistors, diodes, and what do you say, diodes. And apart from that, we use a lot of oscillator circuits. We can make a timer circuits on extremely small chip design. So usually the external connections are made using the current connection will be having a there itself external connections on a single chip of silicon, and the interconnections are also done at the same time. So what is the use of making the integration? Very many advantages are there for using this kind of integration in our components or in our circuits or in the devices. So the advantages are, they are extremely small in size, they are small weight, low cost, low power consumption, high processing speed, and easily can be replaced also. Very easily you can design a chip, or very easily you can devise a circuit. And there are several major steps that are included to make this kind of integration circuits. So major steps I have given here. One is you can see here, the first, you are taking a silicon. For example, you want to have a silicon wafer, silicon chip. You take a silicon crystal. The silicon crystal cannot be directly used to make this kind of integrated circuit. First of all, you have to process it. You have to cut it, like by using some kind of chemical techniques we will do that. So it should be cutting down like a wafers, like like a bread slices. You have a sliced one, like you have a like layers. So like that you have to cut it down in the form of layers, and then you have to have grow and by using some kind of chemical reactions, chemical techniques, we have to do it, clean it, purify it, and because to avoid any kind of defects, to avoid any kind of dust, and without any pollution, we have to go for masking, and then we have to dope them so that the conductivity, it will act as a platform and support the conductivity, and you have to make it strong. You should not be like a malleable. The doping is mainly done because to increase the strength of the material, reliability, and and increase the hardness, so that it will withstand to any kind of environment, So these are some of the major steps which are included in getting an integration fabrication on an extremely small chip of silicon. Now coming to what do you mean by very large scale integration? So right from our school days, we are listening, the first electronic computer is there and it occupies huge room, and there will be lot of electronic circuits will be there, lot of you have to handle a large number of circuits at a large and occupies a large area, and the speed will be very minimum. And so this kind of situation is there in the year 1946. But after that, as the days are progressed, the people started working on the chip designs, people started working on the motherboard, people started working on the components which we are using in the motherboard or in the integrated circuit. At the material level, at the component level, at the device level, they started working, and the conversion you can see in the form of a laptop. In the 2000, in the 1990s itself, you can see the laptop. But after that also, the Apple has made our life very easy by coming with a touchscreen technology in the 2000, and it has introduced that Apple computer, and the kind of design. First of all, we can say there is a lot of difference when we look at the Toshiba laptop, which come in the year of 90s and 80s, and to the Mac Pro book, which was developed by the Apple, because the market only teaches us a lot of things nowadays, and there is a lot of huge development in the technology. You can see there is a touch screen technology. You can store the large amount of data, you can retrieve the data very well at a very short span of time. I think no time will take. And the touch screen, like you use your mobile phones, you press or you give some kind of programming, some kind of order. You want to open a messages folder, you just touch it. Within no time, the messages folder will open. You touch the WhatsApp icon, the WhatsApp messages will be popped up on your screen. So this kind of touch screen technology mainly developed by the Apple, but this is all controlled on the back end, door, on the back side of every device by the VLSI and the integrated chips and the components which we are using, and whatnot. Everything was controlled by the backend data that is hardly corely maintained by this VLSI only. And you can also observe here, I have given you the chip design, the size, when it comes to the generation 1, when it comes to the generation 2, when it comes to the generation 3, you can see 50 co-packaged optics, the 3D with integrated lasers. It was designed on the generation 5. So as the size is decreased, you can observe the efficiency is not decreased. The efficiency each and every time when we coming from the generation 1 to generation 2, generation 2 to generation 3, and 4 to 5, the efficiency is developed. The storing of the data was developed. The speed has increased. It is occupying less space, less weight, less mass, and the no time gap between the retrieving and saving the data. Loads and loads of information can be stored inside the chip, inside the whatever the device we have, and the efficiency is increased 10 times. Each and every time as the size is reduced, the efficiency is increased like anything. The efficiency is increased like anything. So this was only presented by the Moore's law, where as the years are passing, the number of transistors which on microchips is doubling every year, is doubling for every 2 years, it is doubling. So innumerable number of transistors are used on a microchips every year, and because of that, the whatever the memory, the timer, or the circuit design, or the heating elements, or thermal part, electrical, electronic, whatnot, everything was maintained for over a period of years without any difficulty, and you can also see there is the Intel has given, see, we have started our journey when the size of the chip, when the size of the circuit is in the angstroms range. Angstroms means 10 power minus 8 angstroms, 10 power minus 8 centimeter, 10 power minus 8, or 10 power minus 10 you can consider. But as the years has passed, right from angstrom, we have started from the 3 nanometers, 4, 7, 10, okay, like that we have come down to 65 and 90 nanometers. In all these years, the size of the chips which we are using, either in the metal oxide field effect transistors, or you are using bijunction transistors, or using the NPN transistors, or the channel length of the NPN transistors, or the diodes, whatever you take, the channel length has been decreased. So thereby the efficiency, it is the size of the transistor is decreased, in the sense the channel length was decreased, and thereby the channel length was decreased to 65 nanometers, the channel length was decreased to 90 nanometers, the channel length was decreased to 65 nanometers. So, and the size decreased, the efficiency is doubled. You are able to overcome so many hurdles, you are able to overcome so many disadvantages, and can make the device to work very well equipped with any kind of environment. For example, you can take some kind of materials are there. You consider the same Toshiba laptop example. When you are holding that laptop for so much of longer time, when you are holding that laptop for so much of longer time working, or when you are talking on a mobile phone, let me put in this way, which will be very easy for you to understand. You are talking on a mobile phone for a longer period of time, more than 45 minutes, 50 minutes. The heating efficiency, the heat will start generating from our ear. The heat will start generating from our ear if you take a 5,000 rupees mobile phone. But the same way, when you are going for a 65,000, 70,000, 80,000, 90,000, or 1 lakh, 1,50,000 mobile phone, you go for a Samsung, or you go for an Apple, you go for or whatever the company you name as the like high end mobile phone you are trying to go, the kind of materials, the kind of the integrated chips they are using, the kind of design they are doing on the motherboard, or on the chip design, whatever they are doing, it is making us that heat will be absorbed. The fans or the coolants, whatever they are using, automatically the motherboard or the circuit itself will start reducing the heat energy which was generated, and so thereby we are safe whenever we talk for a longer period of time. Yes. Now coming to the scaling. Am I audible? Am I audible too?
Yes, madam.
Okay, thank you. So the scaling, what is actually we are facing the problem in VLSI? The scaling has reduced the power consumption, low power losses. You can see when the material or the chips was designed in the range of, when the components were designed in the range of 65 nanometers, there is some kind of power loss. But when the size of the components or the size of the integrated circuits, the transistor chips were designed to the 28 nanometers, 50% of the power losses was coming down. And this was reported by the scientific community only. This is not mine. This is reported by the scientific community. And the 14 nanometers, it was 80% loss. So less power consumption was observed in this. So, and moreover, millions and millions we are going to fabricate on a single chip. So what happens is at a time you will get on board the 8 cores instead of one using in the same space. So one core I'm using, in this one core I'm using the eight cores of the transistors or logic gates or the devices or the systems was developed in the same space, and I'm getting 3 times faster the device will work, and 10 times the power consumption can be decreased. So this is scaling down the size, the scaling down the channel length, or the scaling down, you take the size of the transistor, NPN transistor, or the scaling down the PN junction diode, or scaling down the resistor, capacitor, whatever the 8 pin chips or 12 pin chips, whatever you use, you can decrease that, the area will be very much decreased. So mainly this VLSI domain consists of 3 important parts: design, CAD tools, and technology. So in that, the nanotechnology plays a role in the design part. So in the design part, there are a lot of steps are included, like a system specification. All of you may be aware of this. This is a fundamental procedure followed. So system specification, or you can see architectural design, functional design, and logic design, circuit design, physical design, fabrication, packaging, and testing. So this VLSA mainly design, making, and testing integrated circuits. It plays a huge role, and the design is comprising of so many steps. So in this design, we are using integrated chips like 100,000 logic gates. We are using 10 lakhs logic gates. We are using on a single platform, single silicon chip, and making it enabling to work. Connections are done. Current controlling devices are used. Oscillators are used. Amplifiers are used. Sound systems are used. So if we have any problem, a beep sound will be coming out. So this kind of design was done in this design part in a VLSI. So the factors that are considered in VLSI design, mainly it integration improves the power, the speed, the size, the cost, and at a larger level, like 8 cores you are using in a small space, this will reduce the manufacturing cost also. This kind of integration reduces manufacturing cost also. So thereby, so many advantages are there because of this kind of reduction. Sizes for circuits, increased cost effectiveness for devices, and improved performance, operating speed and circuits, requires less power, higher device reliability, requires less space, and miniaturization. So these are all the advantages because of that we are of this design kind of design. And but at the same time, you will have challenges in the circuit level. So shrinking geometries, lower power voltages, higher frequencies, negative impact on reliability. Shrinking geometries, low power voltages, higher frequencies can be managed by using the nanomaterials while making the NPN transistors, PN junction diodes, electrodes in the capacitors, electrodes in the capacitors, or in any dimension, 1 dimension or 2 dimension or 3 dimensions. You can change the system, you can control the power losses, you can actually control the electrical losses and power losses. And in the kind of a design, there is a lack of appropriate area, challenge is there, speed is there, power is there, and the area of knowledge of specialization and knowledge should also be there. In this, these kind of challenges arise in the VLSI design. So the now what exactly the correlation between the VLSI, the nanotechnology, and I have given as a NEMS. So first of all, VLSI means these are integrated circuits, millions and millions of transistors, 100 lakhs of logic gates are integrated on a single silicon chip. And what is a nanoscience and nanotechnology? Nanoscience and nanotechnology is nothing but reducing the size of the transistor and making it more efficient to work. Although you reduce the size of the transistor, by reducing the channel length in channel metal oxide semiconductor transistor. So, as I told you earlier also, it is affecting the channel length. So, thereby several thousands of transistors are fabricated on a single chip and speed can be enhanced. So, this NEMS nano electromechanical systems is an area in nanotechnology, that is devices are built on advances in nanotechnology. So what are the uses, advantages to overcome the challenges in VLSI when we use these NEMS devices? Work in nanoscale dimensions, low mass, because as you are decreasing the size, there is a decrease in the mass, there is a decrease in the weight. So as I told you, you can hold a Toshiba laptop, a Mac ProBook. Mac ProBook nowadays in the market, you can observe very lightweight. It is like our notebook only, but works very efficiently. Works very efficiently. You have all the technologies in that book. So don't misunderstand that I'm always comparing Mac ProBook, because students and faculty will have a larger view of that technology to make specifically. So I'm taking that as an example. And it can operate at higher resonance frequencies. So one of the challenge in VLSI is working at higher frequencies and speed, and working in all, able to operate in all the environmental conditions is also one of the challenging area in the VLSI. So that can be overcome by using these kind of NEMS devices. Already it is in use to some extent. And reducing the size of chip at nano level will decrease the area of fitting the components. Size will be reduced. Power losses can be decreased. See, when we are talking about the power losses, we are talking about millions and millions of transistors. So fundamentally, when we talk about a transistor, it is nothing but either PNP transistor or NPN transistor. And PNP or NPN transistor, fundamentally, again, it is nothing but PN junction diode. And PN junction diode, how you are making it, either using P-type semiconductor and N-type semiconductor. So you are using a semiconductor material, P-type and N-type. There, then you are bridging to P and N. Then you are bridging to two PN junction diodes. You are getting a PNP transistor and NPN transistor. So like that, you are bridging the materials. From materials, you are building the blocks. From materials only, you are building the blocks. So if that material is made in the nano range, the already the scientific community has reported, lot of research work is going reported, and a lot of research work is also going on in this area. So material, you are considering semiconducting material, P and N type, P and N type PN junction diode, PN junction diode PNP transistor. Those kind of PNP transistors also you are decreasing the size. So thereby lots and loads of transistors you can load on a single chip. So thereby, since the size is decreased in the nano level and the material is also decreased in the nano level, so the power losses will be holding on, and the power losses can be decreased, and you can control the power, you can control the electric losses. So able to work at higher frequency regions also, and speed can be increased. So these nanostructures I have mentioned here, this you can see the zero-dimensional nanoparticles, one-dimensional nanorods, two-dimensional layer sheets, three-dimensional balls. Balls means three-dimensional spherical balls. Three-dimensional spherical balls. Any of the structures you can make by using any of the different techniques. So many fabrication techniques are there. So these nanostructures, again, they can be divided into passive nanostructures and active nanostructures. So in these passive nanostructures, you can consider the nano coatings, nanoparticles, nanostructured materials. See, nano coatings we are seeing everywhere. In our television, you see the ad of an Asian paint. You see the ad of an Asian paint. What they say is the dust repellent Asian paint, you can use them, and next to the railway track also, it is not going to hamper your are getting polluted. So why? Because after preparing the Asian paint in a lid of the box, they are using a nano liquid, which is a dust repellent, because nanoparticles are having one of the properties hydrophilic in nature. Hydrophilic in nature. And I can also say that one of the best example is a lotus leaf. Lotus leaf is also coming under that category only. It is having the nanophilic in nature. In nature, so many nanoparticles are there, nano objects are there. Maybe we are not that much aware of them, and we are not able to connect to them in the nature. And nowadays, the nanoparticles, nanostructured materials, the textile industry is progressing in this direction. The textile industry, if you go for a Coimbatore, which is a majority production is there from the Coimbatore, the textile industry, what they are trying to do is the threads, whatever they use in the weaving of the silk material, or in the weaving of the cotton shirt, or in the weaving of the silk coat, whatever, they are making that silk threads in the one dimension threads or two dimensional threads. So what happens is, if somebody pours a coffee on our shirt also, it is not going to stick to our shirt or sari, and there is no need to wash them also. So coming to the active nanostructures, these active nanostructures, you will have the nano machines, self-healing materials, nano electromechanical systems, targeted drug delivery. So in these active nanosystems, the systems or the devices comes into picture, and here the materials comes into the picture. So here we are talking about the nano electromechanical systems, which is nothing but NEMS. Now coming to the how, as I told you that the nanomaterials, the size of the nano transistor, apart from the size of the transistor, the nanomaterials which we are using inside the transistor plays a huge role to overcome the challenges in the VLSI. So while making components, the materials are used at the nano level. These materials play a key role in the efficient working of devices, and these materials can be prepared very easily by using different kinds of techniques. For example, diamond. Diamond is a very hard substance. It can sustain hard environments also. Carbon nanotubes, nowadays they are used everywhere in the tennis court, in the rackets, everywhere. They are light in weight, very high in strength, flexibility is there. Silicon, gallium arsenide, gallium nitrate, gallium arsenide. These are all several, some kind of materials which I have provided here. And why this is happening, the main theme is why this is happening for the nanoparticles. Why we are saying that as the size is reduced, efficiency is increased. What is that happening? Why it is happening? And because the more number of atoms are there on the surface, more number of atoms are there on the surface. So highly all the atoms, so if there are 100 atoms are there on the surface, 100 atoms will be playing the key role in the or providing the electrical conductivity. If only 2 atoms are there on the surface, 2 atoms only will give the electrical conductivity. So there is a lot of difference in the ratio from macroscopic or microscopic to the nanoscopic scale. So the physical properties of nanoparticles which changes are the size, shape, surface area, aspect ratio, agglomeration, size distribution, surface morphology, structure, solubility, color, density, hardness. Hardness is one area where we have to really really it is a very important aspect because the in the nanomaterial, you can make it to able to operate in all the kind of environmental conditions. Melting and boiling point can also be controlled. These kind of properties, physical, not only physical properties, I have mentioned physical properties here because these kind of properties are helpful in the VLSI design. But chemical, electrical, mechanical, magnetic, all the kind of properties can be changed when we use these kind of nano structures or nanoparticles in the making of devices, in the making of systems. So in which aspect it is going to use. So here I can mainly I want to focus on the mechanical properties and the electrical properties. So the electrical conductivity of nanomaterials could also be increased, could also be enhanced appreciably due to the better ordering in the microstructure, and at the same time the kind of heat energy or the kind of frequencies they can withstand, and they can become more reliable, more hard, more strength and feasibility and flexibility can also be maintained in the case of mechanical properties, because the surface area to volume ratio, which I have shown as a third slide in my presentation, the surface area to volume ratio, more number of atoms on the surface will be acting, and so more number of atoms will be participating in the electrical conductivity, or to maintain strength, or to maintain that hardness, or to withstand the temperature changes, frequency changes. So these two are the mechanical properties, and electrical properties are the main core for the NEM devices. So this is the nanoparticle surface, shape, size, material. So a nanoparticle, when you are coming from 100 nanometers to 1 nanometer, the surface will be modified, the shape will be modified, the material, different designs, any kind of material you can prepare at this range, and the size can also be modified by using different kind of techniques. And there are several applications are there, of which I have projected here, which are related to the electric and mechanical, electromechanical systems, and there is a lot of chemical reactions taking place, and electrochemical reactions are taking place while preparing these devices, while preparing the chips, or integrating chips on a single layer, integrating chips, several thousand transistors on a single layer. So coming to the NEMS now, what do you mean by NEMS devices? NEMS, nano electromechanical systems, deals with electrical and mechanical functionality on the nanoscale. So this is coming from the MEMS devices. So initially it is at micro level. Now we have converted them into the nano level. And here I have presented here one of the multi-chip integration and system on chip. You can observe here how these wafers are going on. The channel metal oxide semiconductor materials, and you can see how this printed circuit board is there. Printed circuit board is the next generation, because for this printed circuit board nowadays conduction ink is playing a major role. I want to show that how that conduction ink was prepared by one of our student team, and recently they have presented their paper in the international conference and going for a Scopus Index journal also. So this printed circuit board, like there will not be any components in this printed circuit board. There is no connection between the components in this printed circuit board. Everything is done like you write down something with the conduction ink. You write something on a white paper, you take and you write something with the conduction ink. You write your name, you write your EC department, Electronics and Communication Engineering department. And with that conduction ink, the current starts flowing, and you can, depending on its voltage, depending on its regulated voltage, you can switch on the LEDs also. You can switch on the LEDs also. You can try that. And this 3D packaging, and this is one of the interesting area where the layers, they have taken the layers, like I have told you, when you are laying everything on a single silicon chip, you cannot dump at the macroscopic level. On a single chip, the area is very less, and you have to reduce the scale of the components to that level only. So reducing the size of the components and increase without disturbing its working conditions is a challenging part, but not a difficult one. It is an easy only. The different types of fabrication techniques comes into picture in this kind of making of the devices, multi-chip integration and system on chip integration. So several materials are also several components, several materials. For example, you are considering a PN junction diode, you are considering a transistor, you want to build a logic gate. You want to build a logic gate. So NAND gate, NAR gate, AND gate, whatever the gates you want to build up, you are going to have a device, a chip or a P-type and N-type or a gate which can act 1 0 or 0 1, whatever the output you want to get. I'm telling you is, you prepare a material. You prepare a material at the nano only. You, instead of you reduce the size of the transistor, but at the same time reduce the kind of a material which you are using to prepare the transistor, to prepare the transistor, to prepare the diode, to prepare the capacitor. So that material, and along with the size of the transistor also you reduce, then all the challenges can be very well overcome in this VLSI designing or integration chips designing. So some of the materials, majority of the materials which we can use them as a silicon carbide, carbon nanotubes, gold, platinum, to name a few. Silicon is the best material employed in integrated circuit technology because all of them are laying on the silicon chip only. It is there with the MEMS as well as with the, it is there with the NEMS also. So because it is feasible, manufacturing cost also will be very less. Area can also be, you can easily make it as a layered material from the silicon crystal structure. Now, this NEMS devices can be fabricated in two ways. One is a top-down approach. Top-down approach means building something by starting with a larger component, like you have taken a rock and you have made a sculpture. So with a larger and carving away material like a sculpture. So rock to sculpture is one of the technique, top-down approach. And bottom-up approach means building something from by assembling smaller components. This is one what I'm talking, like a brick to building. So like a car engine, atom by atom assembly. You take first of all you work on the semiconductor materials. So in the semiconductor materials, we have intrinsic semiconductor, extrinsic semiconductor. You take extrinsic semiconductor because, as you know, extrinsic semiconductor is more pioneering than intrinsic. So in the extrinsic semiconductor, you consider P-type semiconductor, N-type semiconductor. And those semiconductor materials you take in a periodic table, 3, 5 or 2, 6 materials, and prepare them by using different types of techniques to reduce the size of the particles, Like the best example is germanium and silicon. You take a silicon structure, it is at the macroscopic level, reduce it to the nano, and use them in the fabrication of PN junction diode or PNP transistor. Their 50% job is done. Then you fabricate that using a transistor, and you fabricate using that powder as a diode, or you use them as a one of the anode or cathode material in the capacitors. So that will make your job easy. But provided certain conditions, certain rules need to be followed for this kind of fabrication to reduce from the microscopic to nanoscopic or macroscopic to the nanoscopic scale. So I have given one slide over here where the key parameters for the synthesis of the nanoparticles. If we can do this, we can prepare a nano powder, nano material, so that we can use them as in one of the anode, one of the cathode, or one of the electrode, or one of the P-type semiconductor, or you can make N-type set, whatever you want to do, you can do that. But you can make them in a 4 walls room. Like the majority of the most important factors which we have to consider is the pH of the solution, and by controlling the power of hydrogen, pH value, I think I have given here, you can control the size of the material. And the second one is temperature of the reaction medium determines the nature of the nanoparticle form. Like is it 1-dimensional, 2-dimensional, 3-dimensional, spherical shape, square shape, dot shape, whatever the size, shape, or whatever you want to require, you have to have a control on the temperature. And the quality type of the nanoparticle for which the reaction undergoes, that is also very important. And each method has an advantage and drawbacks also, but the majority of the parameters is time, temperature, and pH. If these three parameters you can hold on and control and have a like a kind of a step procedure, definitely it is very easy to prepare the nanoparticles and nano powders. So there are several methods are there for the nanoparticles: physical, chemical, and biological methods are there. And in this, the methods are physical methods. Several under that, several methods are also there. Biological methods. So any of the method which you feel feasible, any of the method which you feel comfortable, you can use them. But at the same time, there are some challenges are there which you can control them at the time of synthesizing the material. So what exactly these NEMS devices will act in the VLSI? This is the actual core part, because the nano electromechanical relays, I think you have heard about the actuators, sensors, on a nanometer scales they are built in, and this nano electromechanical relays, they are 3-pin or 4-pin terminal configurations. And the when we are using large number of transistors at a microscopic level or in the MEMS devices, there is a leakage of the current, and the efficiency is also limited. You cannot go beyond that efficiency. But by using this nano electromechanical relays, on and off start can be maintained very easily, and significant will have a control on the on and off state, and the transistor leakage is controlled, and you can have whatever the efficiency can be increased very well. And the second important application is field programmable gate arrays. So this is a FBGA. This is a zero leakage current, low energy usage if you are using, and you can use the switches as a switches like a channel metal oxide semiconductor place. You can use them as a routing switches, and you can use as a static RAMs. Power leakages, chip area can be is minimized, power leakages are controlled. So this is also one of the field programmable gate arrays is one of the device where they can be used in the integration of the device. The next important one is the NEMS sensors. So I think now we are going towards the 5G technology, 5G infrastructures, and lot of sensors are used, sensing technologies like a pressure sensor, temperature sensor, face recognition sensor. Everywhere the sensors are used. And the best part of these sensors and actuators is they can we can depend by controlling the material, by controlling the particle sizes, you can control, you can operate whatever the required voltage you want. You require voltage you want. For example, this IoT, Internet of Things requirements under 5G infrastructure, conventional, they are using a round of evaluation. Now this is going as a hot topic in the scientific community, and you can use this as a I have given several pictures over here which are using as a NEMS accelerometers. So what is this NEMS accelerometers is like it can slight deflections or stress deviations through electrical signals. And for example, this I think you can observe in the high-end cars like Audi or Skoda cars, where there is some change in the engine, the car will stop automatically on the road. Maybe that is the high end and electrical vehicles. For example, you are going too high, or you are going in this Audi cars or cars we are using. If there is a slight disturbance, or if there is a heavy traffic, the music which we are listening will be automatically controlled. There is no need for me to control the music if there is a traffic, and if I am not accelerating. So slight deviations in the stress, slight deviations in the electrical signals, slight deviations in the pressure signals while accelerating the car, this and gyroscopes, resonant gyroscopes like sound navigation, optical navigation, and during this was oceanography. This subject is gyroscopes are mainly related to the oceanography area, where you can widely used in various electronics and navigation systems, like you can direction sensors, direction sensors, magnetic sensors. We are using this NEMS gyroscopes. And acoustic sensors, I think you are using in the smartphones and speakers. Smartphones are the best book for us to understand the best VLSI, to understand the materials, to understand at the fundamental level. You are in all our hands. We have a smartphone in today's world. So that smartphone teaches us a lot of things. So that sensor smartphones, the acoustic sensors are used in the smartphones and smart speakers. And gas sensing devices. Gas sensing devices means these are operatable in all the kinds of environments. These are operatable in all the kinds of like alarming system is done when some gas is leakaged in the industry side or factory side, or in the academic institutions also, if something is happening, there will be one alarm in each and every floor where the alarm starts getting into. And if there is if these kind of gas sensors or gas sensing machines are used in a very large device. In a very large device, you take a ship, you take aircraft system, you take you take a spacecraft system. These sensors are very well in use. So the NEMS devices, more or less, I can show here the nano generators. So these nano generators, nano robots, nano motors are again carbon nanotube nano motors. These are made with carbon nanotubes. The name itself is like nano motors or nano generators itself means that the materials which we are used, whether it can be 1 dimension, 2 dimension or 3 dimension, the carbon nanotubes are used. And NEMS based transducers, accelerometers. And coming to the bio-NEMS is one large area in the medical device applications where they are using in the medicine, life sciences, nanorobotics, and which can have potential to function as proteins, DNA, and nanoscale autonomous robots. So I can show in this picture where there is a nano generators. You can see that how best they are operating in, how best they are covering in all the areas. So in all these devices, in all these systems, you take an electronic device, you take a computer device, you take any kind of device. Electronics is the major component. Functioning, programming that electronic components is another aspect. So that kind of controlling that electronic part, that controlling the heart of a human body, like that is a major challenging issue. And in all these devices, the materials which we are using, fundamentally, the step one is the material. What kind of materials you are using? For example, I cannot every time depend on the silicon or germanium. I have to go for, depending on my efficiency, depending on the output requirement, I have to switch on to the different kinds of materials. So in that, when compared to the conducting and insulating materials, semiconducting nanoparticles has a huge applications and advantages in this nanotechnology or during the preparation of nanomaterials. And dichalcogenide materials are another one. Mixing structures are the third one. So every material has its own nature, and the combination of 2-3 materials gives a best output depending on our requirements. So in that, the semiconductor nanoparticles, if you are considering gallium nitride, gallium phosphide, indium arsenide from 3,5 group, and 2 and 6 group semiconductor, combination of compound semiconducting elements and elemental semiconducting elements, these are majorly used, like zinc oxide, zinc sulfide, cadmium seleride, cadmium telluride. So in photocatalysis, electronic devices, photonics, any kind of devices, modern devices such as computers, cell phones, televisions, anywhere these semiconducting materials are used. So in these semiconducting materials also, there is a chance that losses will take place. So for that, we are switching to the wide band gap materials. So wide band gap semiconducting materials means usually For a semiconductor, there will be a conduction band, there will be a valency band, and the band gap is 1 electron volt, like that we say. But this wide band gap, when you are preparing the semiconducting materials at the nano range, the band gap is increased. So people think that, oh, my band gap is 5 electron volts, so it is no more semiconductor. No, don't think in that way. Although your band gap is more than 1 electron volt, it can act as efficiently, and that name is nothing but wide band gap semiconducting materials. Higher breakdown electric field, higher operating temperature capability, excellent thermal conductivity. This is where we have to work, because heat energy will not be generated continuously and can be operated at higher power and higher frequency. So this kind of characteristics are observed in wide band gap materials. And you can see these are the materials which I have listed, or I have given here. These are all related to 3, 5, and 2, 6 elemental semiconductors and compound semiconductors only. And these are all used in the photocatalysis, photoelectric effect. And for all these things, there is again integrated chip design is there. There is again a motherboard is required. There is again a very VLSI design is required. And in all these designs, again comes into the picture the transistors, logic gates, Boolean algebra comes into the picture, and maintaining them and having a proper connection, giving a proper conductivity. And again, these materials plays a key role. So now coming to the what are the applications over this? Aluminum nitride is an attractive surface acoustic wave devices because of this wide band gap semiconducting materials when you are using in the making of devices, in the making of NEMS devices, in the making of transistors, or in the making of IC chip, integrated design circuits. And the second one is power switches, compact power switches for power distribution, automotive, industrial applications. And what happens is the energy losses can be minimized. The electrical losses, 60% of the electrical losses are happening at the industry and the factory because of the different types of materials which we are using, different types of because of the transistors or because of the integrated chip design. So these kind of small changes in the working or in the fabrication of any kind of designing a circuit or in the large integrated circuits may cut the energy savings to 10%. And on and off state of the transistor can also be controlled. And silicon single wall carbon nanotubes are the one majorly they are used in all the electronic devices, optoelectronic devices, and the electronic devices also. One of the last applications which I want to present here, this is nothing but the solar cell to a PV system. So again, the solar cell, solar array, tracking system, mounting, calibrating, generation meter, battery, fuse box, and this kind of system should be maintained for maintaining a solar cell or to a PV system. And for this, again, one device is required, one motherboard is required, one integrated circuit chip designs are required. So this, when the higher part of the solar energy spectrum is absorbed when we are using the nano semiconducting materials, and higher value of the output voltage of the cell when these kind of wide band gap semiconductors, especially at the nanoscale, if we are using them. And these are some of the applications which I want to just look at a glance, where the market end use automotive industry, the materials are used these are the materials, the applications, all the electronic devices which we are using. And you can see consumer electronic devices, converters, automotives, renewable energies, power distribution, UPS, all the devices are having this VLSI. And in this VLSI, challenges are there, but these challenges can be overcome if we can work at from the material to the size of the transistor as per the Moore's law. So in that material also, we have to specifically and keenly, we have to study the material and see its advantages and uses before to convert that into a device. Okay. These are the possible new applications: smart power control, smart cars, smart house, information technology, solid state lighting, medicine and defense. And with this, I end up my presentation. And this is some of the slides where one of my student team has prepared the nanomaterials that was prepared. And this is for the using the sol gel technique. This is one of my major work which I am working on, this gallium nitride, which is a 3-5 semiconductor, which can be used for the photovoltaic applications, and it has come to be wide band gap semiconductors also. And this is one of the other team of my students, fourth year major project students. They have prepared this nanomaterial in my lab. So the color was changed, and which can be used. This is a kind of a mixing structure. Mixing is one of the material nowadays. Mixing structures or material structures are one of the materials nowadays. They are having high importance in to use them as an electrode materials. Like you take battery, you have a anode and cathode. You take capacitor, anode and cathode. You take supercapacitor, you have a anode and cathode. So that anode or that cathode materials, nowadays they are preparing with mixing structures so that the efficiency will be increased to a higher amount. So this is one. This is my another one work which was done by the mechanical engineering students in my lab. And this is what I'm talking about. We actually prepared a conduction ink for this. I have presented like a paper electronics system, which I have told you. When you this is an index, this is ink which we have prepared, and we have taken a multi-wall carbon nanotubes powder, and using the gum arabic we have prepared this material. But we have taken the different ratios of this conduction ink. So when you can use them in the printer in the form of cartridge, or you can depending on the pen's availability and the thickness and the thickness of the liquid we can use them in the pen. And otherwise you can take as an ink pillar, and you can start writing on a white paper. And depending on the resistance, voltage and current as per the values, you can use for whatever the devices you can take. So this is going to be a future trend. Now the components will also maybe after 8 years or 10 years, maybe of the components will also start slowly getting washed away, and everything you are getting on the paper, and everything you will replace with the paper only. The paper consists of depending on the thickness of the paper. Since the paper is a cellulose material, you can use a kind of a salt solution, and you will have an anode and cathode. You can use them as a paper battery. Otherwise, you can use them in the paper means of electronic circuits, to design the electronic circuits on the paper itself. So this was one of my student team has done this project last year. I mean this year. This year they have submitted in the month of May. These are the team members. Thank you very much. Thank you for patiently listening to me. And I thank the Department of Electronics and Communication Engineering HOD sir, Dr. N. Uday Kumar Garu, and Dr. KB Sinduri for giving me this opportunity to share the topic with you. Thank you so much.